introduced to as the Bronsted-Lowry definition. We're going to rewrite it in our notes. It's that important. This process of writing is one tool that we can use to put to memory things that we are exposed to. Just watching a video, just flipping through some PowerPoint slides, those really aren't nearly as powerful tools as writing things, in my opinion. And I've been doing this quite some time. I've taken a lot of classes, a lot more than most of you, and this was a very, very powerful tool, still is. So we know from general chemistry this Bronsted-Lowry definition, or Bronsted-Lowry acids, bases, and maybe it was something you hated and despised, but sadly it's not going away anytime soon. Acid-base chemistry is pervasive in nature. It's pervasive for many of you who are biology majors. Many of you going on to study biochemistry, any types of biological systems, acid-base chemistry is pervasive. You will see it over and over again. So if you feel weak on acid-base chemistry from your past exposure, now's the time to really learn it. Acid, in the Bronsted-Lowry definition, and the definition that we'll use most of the time, is very, very simple. It's any substance that can donate a proton. And a proton in chemistry or organic chemistry is written as a hydrogen atom with a plus charge next to it. It's actually a hydrogen atom that's missing its electron. This has a special name. It's known as a proton. So this little H plus thing here, we're going to call it a proton. We'll see it all the time from this point in this class forward. And a base, very simply, is kind of the complement to this. It can accept a proton. So it's any substance, really, molecule or thing or entity that can accept a proton is a base. Anything that can donate a proton is an acid. It's really quite simple. Just these simple definitions, and we'll contrast them to the Lewis definition when we get there. All right. And let's actually just look at a very, very common example of an acid-base reaction. And you should be drawing all of this exactly as I am. So we're going to switch gears now that we've got past our introductory lessons for organic chemistry. And these little lines that I'm drawing next to atoms, such as on oxygen and water, you might be used to seeing these little dots. We're going to advance from organic chemistry kindergarten and upgrade a little bit. These little lines right here have the same meaning as these two dots here. They have the same exact meaning. It means 2 electrons. And we see these little lines everywhere. Here's the line. This one we know means a bond, and in that bond we know there are 2 electrons. We're not going to draw them as dots anymore. It's just really kind of more of a general chemistry approach. Here there's 2 electrons, 2 electrons, 2 electrons, 2 electrons, all those places. So I put an unfortunate number of dots here. I don't want you to put those dots, obviously, in your notes, so I'm going to redraw sulfuric acid. This is a compound whose structure you should draw a couple times and make sure you can always draw it. Okay. So we're going to do an acid-base reaction with sulfuric acid and water. So we're just going to draw these 2 particular species, and they're going to be in equilibrium. And I kind of ran out of space here. If you want to keep going to the right on your sheet of paper, no problem. But I'm going to draw this right below it. And we actually dump sulfuric acid into water, or mix it with it. Something happens. We take sulfuric acid and drop it into water. We get sulfate, and we get hydronium ion. And we're going to look at these molecules very carefully, painfully so maybe, and slow, and just think about what's happening in these processes, which is the acid, which is the base. We already have heard me say the name sulfuric acid, right? So obviously it's the acid, and then water therefore must be the base. But can we actually look at the product side of the equation and make that same deduction, right? These 2 are the reactants, and as they go from reactants to products, which one loses a proton? This is something you should be thinking yourself while I'm annotating. I'm asking these questions for you to think. Which one of these substances loses a proton or donates a proton? Well, sulfuric acid donates a proton because it's missing one. We can see that it's gone, so it gave up the proton, and this must therefore be the acid. Well, if we can identify the acid, we know the other one is the base, but using the same acid-base definitions, why don't we just look at which one of these substances is accepting the proton as it goes from reactants to products? Well, we can see that water has picked up an extra proton. It hasn't picked up a hydrogen atom with its electrons, it's just picked up a hydrogen without any electrons, known as a proton. This will become more clear as we do more problems, which we'll do many. So just looking at this particular equation, if we have the reagents, the products, we should be able to identify, if we don't know this is sulfuric acid, which you should, hint, hint, we can just look at what happens to it. Well, it lost a proton, must be the acid. The other substance gained a proton, must be the base, just by this very, very simple definition. We call this particular species the conjugate base. It's related to its acid partner through a proton. We call this an acid. And on the other side of the equation, if it's given up its proton, it's known as a conjugate base, just they're related. Water here is a base. And on the other side of the equation, we call this its conjugate acid. Right? This is the conjugate acid of water, hydronium ions. The other key important thing that I want to do, and this is taking a long time, just this little slide, it's very, very important what we're going to do next, is we're going to push our first reaction arrows or mechanistic arrows in organic chemistry. These are everyone's bane, basically, the thing that really trips people up. We're going to do this very slowly, very methodically. And you've already done a little bit of arrow pushing in resonance. The pre-lecture video talked a little bit about some rules for this, or it's just some general common ideas. And we don't really need rules per se, but these arrows that we're about to show mean the movement of two electrons. Okay? And they're going to tell us how bonds are being formed and how bonds are breaking in this reaction. They're going to be useful for every reaction we do in organic chemistry. These are called mechanistic arrows. I'm going to draw them in red. And we'll learn why they're happening in this particular direction. But first thing that happens here, we can see going from water to the hydronium ion, there's a new bond that's formed somehow. And this first arrow I'm drawing here is going to be the explanation of that bond. Water has pairs of electrons, and we know that sulfuric acid is acidic. We'll talk a little bit more about this when we get to the Lewis definition, why we go to this hydrogen. We'll get to it later. But basically, to explain the formation of this new oxygen-hydrogen bond and the loss of an oxygen-hydrogen bond, we're going to use a mechanistic arrow. And the base's electrons react with this proton, and this arrow means movement of two electrons. Okay? It's very, very important. So we start from electrons. We don't start from atoms ever with these arrows. We always start from electrons. Usually it's going to be lone pairs, but sometimes it's going to be from a bond. So here we're forming a new bond between oxygen and hydrogen. That's this one here. We know from what you've learned with Dr. Marine is that hydrogen doesn't want to form two bonds. And so in this process, we start forming a bond. Hydrogen already has a bond, so hydrogen's not going to be very happy. And what happened is that hydrogen gives these electrons to the electronegative oxygen here, and this bond breaks. These two arrows both mean movement of two electrons and movement of two electrons. This first arrow has the added meaning of making a new bond. We're going to make a new bond between this oxygen and hydrogen by sharing electrons. That's this bond. This particular bond is going to break because hydrogen doesn't want two bonds. We're making a new one. The old one goes away. These electrons get pushed to this oxygen, and you'll know, well, maybe it's this pair right here. There's three pairs or three lone pairs of electrons on oxygen here in this process. And so these first two red arrows that we've drawn here and here explain this whole process of how an acid and base react. And I know what you're looking at right now is not intuitive at all. That's absolutely okay. That's why I would recommend rewriting everything we've done here and really thinking about it on your own and at your own time. I think that's even more powerful than watching a re-recording of this or sitting back with your feet up on the couch. I think you should just get some scrap paper, get whatever paper you can, and practice rewriting these things, because I'm going to ask you to draw mechanisms on our exam together. That's basically all our next exams are. And so if you haven't ever practiced this, the first time you practice it is on an exam is not the best strategy. Okay? We're going to just say a few extra things that we saw and repeat from your pre-lecture videos. Strong acids give weak conjugate bases. strong acids give weak conjugate bases. And we could say this many, many different ways. We could say that this is just the converse. Weak bases give strong conjugate acids. This is just something we're going to keep saying over and over again, and you'll realize why we're saying it and repeating it and writing it down. But sulfuric acid is a very, very powerful acid. Hopefully you know that from general chemistry. If not, I'm telling you now, so you should know it now. This is a very powerful acid. Its conjugate base is going to be very, very weak. Water, last time I checked water, I drank some this morning, is a weak base. Okay? Its conjugate acid is very, very powerful. This idea of strong acid, weak conjugate base, that is an important idea. Or weak base, strong conjugate acid, it's an important idea for us.